This talk is about the summary of the work summary of the research work that we did in the paper. Right? Yeah, so the motivation for the talk is that when you look at real world data, right? So some of the real world data can be modeled as networks, also called as graphs. So for example, we can model a social network as a graph in which user accounts can be modeled as nodes, and all the friendship, for example, in Facebook, or maybe follower relationships in Twitter, they can be modeled as edges, right? So we have this set of nodes and set of edges, kind of a relationship, right? So they can be modeled as graphs. And to give another example, we can have a document citation graph in which documents are actually modeled as nodes. And if a document cites another document, there will be an edge connecting the two nodes, right? So this can also be modeled as a graph. And we can also model molecules as graphs in which atoms represent nodes, and then all the chemical bonds between atoms represent edges, right? So all of these relational data sets can actually be modeled as graph structures, right? And interestingly, so all of these data sets also come with node features, which are actually intrinsic to the node, right? So when we look at a social network, so each user account, right, will have their own user profile, right? So that will be the node features. And for example, in the document citation network, so documents will have their own content, right? So document abstracts, so they're actually the node features. And then the atom identities, so the identities of the atom, maybe hydrogen atom, oxygen atom, they're actually features of the node, which are kind of intrinsic to the node itself. So in addition to the relational structure, we also have access to these node features. So they also come with node features. Right? Now, the main goal in the work is to learn some patterns from these two sources of information, so the relational and the node feature information. So it's posed as a learning problem. So we want to conduct machine learning over these graph structures. Right? Yeah, the main topic is learning on graphs. So we are given access to V and E, so set of vertices, set of edges. And we are also given access to X, which is the node feature information. So is everybody comfortable with V and E as a graph? Everybody is comfortable, right? Yeah, so in addition to the traditional graph that we are used to, we are also given access to X, which is the node feature information, right? And now the goal is to predict some graph level properties or link properties or even node properties, right? So we are given a graph structure, and then we want to, let's say, do some learning on the graph structure. And then this is kind of projecting all the nodes into a lower dimensional space so that it becomes easy to classify. So for example, this is this blue and orange, right? So there are two classes. So by projecting all the nodes into some favorable representation space, it becomes easier for us to classify the nodes as blue and orange. Right? So this is the problem. So the problem is essentially the node property prediction problem, which is highlighted here. Now, one of the most popular problems in this space is actually the semi-supervised node classification problem, in which instances, machine learning instances, are actually the nodes of the graph, the vertices of the graph, right? So all of these, they actually represent the features, input features, right? So yeah. So in semi-supervised learning, we train with labeled and unlabeled data, right? So we are given some labeled nodes. So the goal is to label the unlabeled nodes in the graph, right? So in so it's called semi-supervised because we use both labeled and unlabeled nodes during the training phase, right? And the main motivation is all the unlabeled data is actually inexpensive. It is freely available. but then it's kind of expensive to label the nodes, right? So it requires some manual labor to label the nodes. So the goal is to use the unlabeled data as well during training, and then eventually label the unlabeled nodes in the graph, right? Yeah, so large volume of, let's say, documents are actually published online. And then they also have noisy labels. So we want to label manually only a few of them, and then use the relational information given by the citation relationships, and then label the remaining unlabeled documents in this citation graph, right? Yeah, so for the document classification problem, let's say we want to predict the labels of a document. So for example, this could be a machine learning document, and this could be, let's say, a database document. And then it has more applications than just document classification. So we can also categorize items in recommendation engines. So we will actually see all the details of the graph in future slides. So we can also classify websites in these hyperlink networks, page-to-page hyperlink networks, and so on. So this is the problem, semi-supervised node classification problem. And now, so the goal of this work is to kind of approach this problem with the help of transformers, right? So transformers have revolutionized natural language processing. So we want to see how transformers can model graph-based tasks like semi-supervised node classification, right? Now, if we look at a traditional transformer, it has multiple components, right? So Professor Raghuram summarized all the components of a transformer in the previous Samvaad talk. So it has all of these components, but the one that we're interested in is this self-attention mechanism, which is a core component of a transformer model. And the self-attention mechanism, it involves the construction of an attention matrix, okay? So all pairwise attention matrix, it is usually used in natural language processing in which all words attend to all other words in the sentence, right? So by doing that, we're actually constructing an n by n attention matrix, right? So we want to focus, so we are going to focus on that attention matrix in this talk. Yeah, so we want to analyze what are called graph transformers, GTs, so which are actually used on graph structures, right? So we have this attention matrix. Now, instead of words, we have nodes, right, representing rows and columns, right? Now, the attention matrix will essentially look at all pairwise relationships between nodes, right? So all nodes kind of attend to all other nodes in the input graph, right? So this is what the attention matrix does. Now, by doing so, because we are looking at every node and every node looks at every other node, we have this n by n attention matrix, which has n squared entries. So there is like a fully connected latent graph, right? So every node is kind of connected to every other node, right? So there is a fully connected latent graph. But then we also have this input graph. So for example, in a social network, the social network itself can be modeled as a graph, which is different from this fully connected latent graph. So we have a different input graph, right? Yeah, so we are given VEX, which is this input graph. Nodes are actually tokens. X has token embeddings, the node features that we talked about. And then in any graph transformer, so V comma E, set of vertices, set of edges. So the graph will actually guide the transformer design. So depending on how the graph is used, there have been different GT proposals, right? So for example, we can modify token embeddings using the graph structure. We can modify positional encodings. Maybe we can fuse the adjacency matrix with the attention matrix. So there are different ideas how to construct a graph transformer, how to use the input graph structure in a transformer, right? Now, so the research topic under investigation is actually a phenomenon that was recently observed called over-globalising, okay? So now let's focus on this latent graph and the input graph, right? So let's say this is node 1, this is node 6, right? So you can see node 1 and node 6, they're not directly connected in the input graph. But then in the latent graph, there is a direct connection because of the attention matrix, right? Yeah, every node attends to every other node, which is inherent in self-attention, right? Now, by having such relationships in this latent graph, so what happens is all of these distant node signals, right? So 1, 6, which are not neighbors of each other, they're kind of overemphasized, right? So because they're not direct neighbors in the input graph, right? So yeah, so in case in the learning problem, let's say 1 and 6 correlate with the labels, then this attention value will be very high. Okay? So by inherently by creating this attention matrix, we are actually kind of having these shortcuts to distant nodes, right? So one is directly connected to 6. So this is a shortcut, right? But this can be a problem. So this can be a problem in some machine learning tasks, right? So that we will see. Yeah. So why are shortcuts bad? So shortcuts can be bad in some contexts. First of all, as we saw, it can ignore the graph context. It will completely ignore this input graph structure, right? So it will base predictions on a random distant node, right? And more severely, it will learn spurious correlations, right? So if 1 and 6 are actually correlated, but then they don't help for the downstream application, so the attention model will kind of believe that these two nodes are actually important for the downstream problem, right? So there are these spurious correlations that are learned by the attention model, right? And then it kind of defeats the input graph's purpose, right? So this is actually the over-globalizing phenomenon, so which is the research topic so in this paper, right? So it's essentially creating these shortcut edges to nodes that are not connected, nodes that are actually more than a few hops away, right? So this is actually the over-globalizing phenomenon that was recently observed, right? But then shortcuts are actually not, its latent graph is always complete because the attention matrix will always have n squared entries. Not because of the over-globalizing, it's kind of inherent in self-attention. The over-globalizing phenomenon is when such edges kind of hurt machine learning predictive performance. It's always learned. There is some weight, there is some non-zero weight on this edge, always. It's never zero. So that's the catch. Yeah, in the process of learning, if there are some correlations, spurious correlations, which are not useful for the downstream task, the attention value will be high. So that is not desired. Yeah, so optimization can only help so much. It is never zeroed out. That is the catch. So it is always a non-zero number. Attention value will always be non-zero. And because of that, there is some bias to connect distant nodes always. So all the examples that we see in this talk are actually cases where the input graph is more important than the attention, than the latent fully connected graph. So shortcuts are not bad always. They can also be good. So this is one slide to summarize why shortcuts can be good. So in some of the models, which are different from graph transformers, so they actually have this local bias, right? So they actually look at the neighborhood of every node. So this kind of, so GT kind of escapes this local bubble, right? So when you have that locality bias, so there is one issue where information can kind of get diluted as we try to get information from multiple hops, right? So that issue is not there in the attention mechanism, right? And in some cases, so these distant connections can also be useful. So in some cases where the node features are actually more predictive than the input graph, so these attention mechanisms can actually be useful. So, and it increases the expressivity of the model. So attention is a well-known idea, so which has kind of revolutionized NLP. So it increases model expressivity. So more sophisticated function classes can actually be learned with attention. So there are also advantages. So we want to strike a balance between not having too many shortcuts, but having only informative shortcuts in this research topic. That's the idea. Yeah, so this slide summarizes the contribution. Sorry. We are not looking at the G, we are also looking at the G, but not directly. So there are actually some graph transformers that are designed where they actually modify some of the components of this transformer block, and the modification is done using the graph structure. But basically speaking, when constructing the attention matrix, we are not looking at G. It could be spurious. That's exactly why it could be spurious. Yeah. Okay, so this slide summarizes all the contributions of this research. So the first contribution is we examine this phenomenon with a new metric that we propose, right? So we call it the K-hop homophily metric. So we'll actually see what are homophilic and heterophilic graphs in the upcoming slides. So now this metric, it kind of measures similar nodes K-hops away, right? So we want to kind of analyze the attention distribution with the proposed metric. So if the distribution aligns with the metric, then we say, yeah, it's good for the task, then it's not good for the task. No, otherwise it's not good for the task. And the second contribution is actually we propose two training schemes. We call this the LocalFormer framework. So we propose two training losses in order to reduce this over-globalizing phenomenon, right? So we jointly train a graph transformer and a local model with what we call a collaborative loss function. So this is joint training of two models. And then in the second scheme, we actually train the local model first before integrating the global model. Right? So that's the second one. It's called warm-up LocalFormer, WLF. This is the second contribution. The third contribution is that we show that these two schemes mitigate this phenomenon of over-globalizing through experiments, right? Real-world experiments. And we conducted experiments on homophilic and heterophilic data sets, so which I'm going to explain. Right? Yeah, so the first type of data set that we investigated is actually homophily. Right? So the guiding principle behind homophily is this well-known proverb, right? Birds of a feather flock together, right? So let's see some examples. So you have these red-colored birds like flocking together. Now the idea here is that an edge is actually formed between two nodes because they have some shared characteristics, right? So in the features or the output labels, they have something that is shared. There is something that is shared. And because of that, there is an edge between the two nodes. Right? And we can have another example like bluebirds. So because they have this shared characteristic, there is an edge that is created between the two nodes. Right? Yeah, so in homophily, so as the name suggests, homo means same, phily means affinity, right? Affinity for the same is homophily. So nodes tend to connect to similar nodes, for example, the same label. Right? So this is homophily. So for example, when we look at a citation network, right? So papers in the same field tend to cite each other, right? So it is kind of homophilic in that sense. Yeah, so it's easy to see that all of these one-hop neighbors are actually highly informative because they're actually similar to the node that we're investigating. And in a perfect world, in an ideal world, a perfectly homophilic graph would be of this form, right? So this is, it is this clustered graph in which so edges connect nodes of the same color, right? So you have this disjoint union of two clusters. So this is one data set type that we investigated. Now the second one is heterophily. So the guiding principle behind heterophily is opposite poles attract. Right? So you can think of a magnet, so like North Pole, South Pole. And edges are formed between two nodes because they have complementary features. Right? That's the idea. Yeah, so nodes tend to connect to others with complementary features. So one example that is usually given is this fraudsters and legitimate account example, in which fraudsters kind of interact with legitimate accounts, right? So they're of different type. So it's a heterophilic relationship. And a perfectly heterophilic graph, so obviously will be a bipartite graph, right? So because it will connect nodes of the different nodes of different colors, right? Okay, so given an edge, can we decide whether it's homophilic or heterophilic? So the answer is no. Just by looking at the edge, it's kind of impossible to determine if it's a homophilic or a heterophilic edge. So the key lies in the attribute, in the node attribute that we are looking, right? So the edge and node attribute as a combination will actually decide whether the edge is homophilic or heterophilic, right? So to illustrate that idea with an example, so let's take this example scenario in which we have this language exchange network, right? So two people interacting in different languages. So maybe, for example, English and Japanese, right? Yeah, so when we look at such a network, so we tend to see people with similar ages interacting, right? And then they have complementary language expertise, right? So when we say that age is the attribute, so this edge between these two people, the interaction, is actually a homophilic interaction, right? Because they're of similar ages. But when we talk about the language exchanged as the node attribute, then this will be a heterophilic interaction because they tend to speak in different languages. So they have complementary expertise. Okay, so this is kind of a nuanced interpretation of homophilic versus heterophilic edges. Yeah, for the same edge, if we focus on a different set of attributes, it could easily be heterophilic. They can coexist from a different lens. For example, if the lens is age, they can coexist. Yeah, it's homophilic. So it also depends on the node properties that we are actually investigating. That's the idea. Okay. Okay, so let's look at some example data sets that we investigated in this research work. So one is actually the Amazon recommendation data set. It's actually this Amazon photo data set. So all Amazon products related to photography, they're actually in this data set. So there is an edge between two, let's say, items if they're actually co-purchased, right? So if they're co-purchased frequently, so there's an edge, right? So this is a homophilic example. So if we look at this Amazon photo data set, so you can see that items of the same type, so for example, accessories, right? So they tend to be co-purchased by a user, right? So it's a homophilic edge, tends to be homophilic. And then I've shown another example. So this is actually this Wikipedia computer science dataset, shortly WikiCS. So this is a page-to-page network. So I don't know if you can see the titles. So this is file system Wikipedia page. This is file system permissions Wikipedia page, okay? So there is an edge between two pages if there is a link connecting one of them to the other, right? So the file system web page will obviously have a link to file system permissions web page, right? So there is an edge between these two web pages. And then the label under investigation is actually the field of this paper. So both of them are actually operating system web pages, right? So it's a homophilic edge because they belong to the same field. And then the third data set that we investigated is actually this co-author computer science data set. It's a collaboration network, right? So authors are actually nodes. And if they have collaborated on any document, there is an edge between two authors. So for example, I mean, obviously authors of the same field will actually collaborate, are likely to collaborate with each other, right? So for example, maybe two database authors collaborating on writing a paper. So these are some homophilic data sets that we investigated in the research. So let's look at some heterophilic edges. So now we are going to look at the same data set, the Amazon data set, but then viewed from a different lens. Now this is ratings lens. Previously it was photography. Here it's ratings, right? Again, it's a co-purchase network. So two items are linked. They have an edge if they're actually co-purchased by a user. So this is a book of Harry Potter. This is like a DVD of Harry Potter. Now, so we are interested in predicting the labels, predicting the ratings, right? So this book actually got 5 stars on Amazon, whereas the DVD got only 4 stars. So they are different, right? So it's a heterophilic edge because they have different ratings. Yeah, so again, in a Wikipedia network, so for example, this Roman Empire, so this is like a curated network. Again, this is Wikipedia page. So if there is a link connecting 2 pages, there is an edge between the 2 nodes. And obviously, in the context of Roman Empire, different Wikipedia pages, like for example, this is Augustus, right? So it's a biographical web page. This is Rome, so this is a geographical web page. So this is a heterophilic edge, right? So they belong to different categories. And then there is a synthetically constructed data set. This is this Minesweeper game, right? So each cell is classified as containing a mine, not containing a mine. So there are 2 labels. And obviously, this is a heterophilic graph, right? So because neighboring nodes, neighboring cells, I mean, 2 cells are linked if they are neighboring. So 2 cells are connected by an edge if they're actually neighbors, right? So obviously, whenever there is a mine, so they tend to be connected. I mean, you can see that, right? So it's a heterophilic relationship. So these are the 3 data sets that we examined in our research work. So heterophilic data. Okay, so let's come to contribution 1. So contribution 1 is proposal of a metric called K-hop homophily. So now this is in plain English, this is the fraction of paths of a certain length connecting similar vertices, right? So we propose what we call K-hop homophily. So homophily is 2 nodes having the same properties, right? So we extend the idea to multiple hops. So K is an arbitrary number. So this is essentially fraction of paths of a certain length connecting 2 vertices of the same label. So this is the mathematical definition of K-hop homophily. So E subscript K is essentially the set of all paths of length K connecting 2 vertices. Okay? Yeah, so what is the interpretation of this metric? So if the metric value is high, then we can say that there is strong homophily between any 2 nodes of distance K, right? If the value is low, then the homophily value is weak. Right? So if the K-hop, let's say the 4-hop homophily between 2 nodes is low, then it means that the connections are weak. So they are unlikely to share the same label. Yeah. So this is like a summarization of. Yeah. Yeah, along the path. Yeah, the numerator has all the edges. Yeah. So u comma v belonging to ek such that yu equals yv. It has all the node pairs. Original graph, yeah. Not in the input graph. In the input graph, yeah. They won't be considered. A similar attribute because there is no k which kind of connects the 2 nodes, right? There is no path connecting 3 and 4. It's the shortest path. Distance k, right? So it is distance k. Distance is shortest path distance. Okay. So this is the first contribution. Yeah, now let's look at the trends on the three data sets that we discussed, right? So these are heterophilic graphs. So Amazon ratings, Minesweeper, and Roman Empire. So if we plot the hop size on the horizontal axis and the k-hop homophily on the vertical axis, so this is what we observe. Right? So to summarize the trends, so we can see that all the data sets peak at k equals 2. So all the heterophilic graphs, they have the highest homophily values at k equals 2. So so nodes that are 2 hops away are actually more likely to have the same label than nodes at any other hop. So that's the idea. And then we can see that there is a downward trend from k equal to 2 onwards, right? So what does this say? So this says that it levels off for higher k. There is no tendency for nodes, let's say connected, I mean for nodes 6 hops away to have the same label. So there is no tendency for nodes at higher hops to have the same label, right? So that is what this plot reveals, right? Okay. Now this is k-hop homophily for homophilic graphs, right? So the three homophilic graphs that we talked about. Right? So interestingly, so in the previous case, they peaked at k equals 2. Here, they actually peak at k equals 1 because they're homophilic, right? So all the one-hop neighbors, they're actually likely to share the same label, right? So they peak at k equals 1, suggesting direct neighbors have the same labels, right? And then from k equals 1, there is a downward trend, right? Again, it levels off at higher k, so revealing that there is no tendency for them to be either similar or dissimilar at higher values of k. So now coming to the over-globalizing issue. So now let's see this k-hop homophily trends. Let's compare them to the attention distribution, right? So what we do here is we actually look at attention k, right? So it's essentially the average. So the average attention value, right, of node pairs, UV node pairs, that are k hops away from one another. Right? So it's the average attention value. Attention k is the average attention value across all node pairs that are k hops away from one another. Right? Now, if we compare the proposed k-hop homophily with this attention distribution, so this is where we can see this over-globalizing phenomenon occurring, right? So you can see, so as we said, it kind of levels off, right, for higher values of k. But then you can see the attention distribution patterns, they're still at a higher level, right? Higher than desired. It's kind of erratic, right? So they go back and forth from high to low, right? So this is this over-globalizing phenomenon. And similarly for homophilic graphs as well, we see that the attention distribution is actually higher than what is necessary for the downstream task. Right? So this is this over-globalizing phenomenon. Yeah, so attention is overly allocated to distant vertex pairs. Right? So distant pairs are actually overemphasized when using transformers on graphs. Right? So this is the over-globalizing phenomenon. Actually, this is part of future work, actually looking at heterophilic graphs, specifically looking at heterophilic graphs, and then looking at attention distributions is actually part of future work. But then here, it's actually more than what is needed, right? For example, this green one, the Roman Empire data set, it's actually more than what is kind of needed. So it's not consistent across all data sets. No, there is no other metric there. There is only attention value. No, so what we do is we train the transformer model on the input task, on the task that we're given. And then that we are looking at the trained transformer model. We are looking at the attention values of the trained transformer. The same task, the node classification task. It's aligned with this k-hop homophily. So whatever metric we proposed on the labels, we use the same labels for actually training the model. Loss is coming because of attention. But then here there is another issue. It's semi-supervised. So we are not given 90% training labels. There is only 5% training labels. So usually in a graph-based setting, only 5% of the nodes are labeled. We have to label 95%, the remaining 95% of them, because they are connected to the labeled nodes, right? So we can use that information. So the loss is not kind of rich. It is not rich in information because we only label 5% of the nodes. Yeah, so within this context, so we have this over-globalizing phenomenon. Yeah, so now we train a graph transformer with a graph neural network, so which is a local model. So just one slide summary of a GNN, right? So it uses the adjacency matrix of the input graph, the normalized version, and then the input node feature matrix. Of course, it propagates all of these across hidden layers. And then we have this nonlinear activation function, and then the weight matrices that are learned during training, right? Yeah, so X0 is the input node features. So this is actually called graph convolutional network, right? And then all of these weights are trained based on the semi-supervised node classification loss that we have, right? So this is the local model that we consider because it looks at the input adjacency and then it only averages out. So this AX operation is like taking the average of all the neighbors of a node. Right? So it's a local operation. Yeah, so to compare the two models, local view of GNN and global view of GT, right? So let's say this is the input graph that is given to us. So now in a GNN, in a traditional GNN, so for example, if this is the node under investigation, so it will receive features from its neighborhood, right? So all the nodes receive information from their neighborhoods. But then in a graph transformer, because of that attention matrix, right? So all nodes look at all other nodes, right? So one receives information from all other nodes, and so does 11. Right? So 11 receives information from all other nodes. Yeah. So this is kind of the difference between this global model and then this local GNN model. So this is contribution 2 of our research. So we actually train the two models together. Right? So one is this collaborative LocalFormer in which we have a joint loss function to train both of them together. So that is one idea. So I'm not going to get into the details of all the math of the loss functions, but this is like the high level idea, right? So we have this collaborative LocalFormer in which we train both of them jointly. And then we have this warm-up LocalFormer in which we train the local module for a fixed number of epochs initially before introducing this global module. Yeah, so local and global modules are trained simultaneously in CLF, which is collaborative LocalFormer. And in WLF, local module is trained independently for initial epochs. And then we introduce the global module. Right? So there is joint training after this warm-up phase. Yeah, so these are some of the details of the two proposals, right? The two training schemes. So I'm not going to get into the details in the interest of time. Yeah, so let's look at the third contribution. So this is summarizing all the experiments in the paper, right? So we looked at the task of vertex classification. So we want to classify each vertex in a graph into one of several labels. Right? So that's the problem. Yeah, and then this phenomenon of over-globalizing, this is specific to vertex level tasks, right? Because we have this attention at the vertex level, right? So attention matrix is actually at the vertex level, right? Yeah, so this is the task, and we looked at several baselines. So all the existing graph transformers, we looked at 10 different GT baselines, And then we compared our proposed methods with all of these baselines. So we did different analysis. One of them is performance comparison. So we compared with the baselines. So we looked at the accuracy on the test set in the vertex classification problem. And then we conducted performance efficiency trade-off analysis. Right? Like this is accuracy, training time, trade-off analysis. We also looked at ablation studies where we removed some components of the model and then showed that all the components are actually necessary. Right? So these are ablation studies. And then we also looked at the attention distribution of this proposal. Right? Okay, so we looked at 5 different homophilic data sets. So these are actually the statistics of all of them. So you can see that they have 13,000 nodes, a few thousand nodes in all of them, right? And then these are the heterophilic data sets, again, a few thousand nodes in each of them. So now these are the results on the heterophilic data sets, right? So this is the test accuracy, the accuracy on the test split for the vertex classification problem. So you can see that the proposed approaches, CLF and WLF, they outperform all the baselines by like 1 to 2% at least. So again, we see similar trends on homophilic data sets as well. So 2 of them, so this one baseline turns out to be the best performing model. So generally speaking, so it's actually effective at predicting labels on the vertices for the vertex classification problem. And these are some ablation analysis. So we looked at the best baseline, state-of-the-art baseline, and then we looked at each of the 2 modules in isolation. So the local one, global one, and then this joint WLF scheme. And you can see, so this WLF is like the best performing when compared to these ablated baselines. So across, so these are 2 heterophilic, 3 heterophilic and 1 homophilic. And then this is analysis of warm-up in this WLF model. So this is the number of epochs. We actually train the local model. So you can see 10 epochs, 50 epochs, 100 epochs, and so on. And interestingly, 100 epoch warm-up is like the best performing epoch number, right? So for all the WLF variants. And then we also did ablation analysis on the CLF model. So this is collaborative joint training of 2 modules. And then we see similar trends here as well. So CLF, so yeah, CLF outperforms local module in isolation and also global module in isolation. And then this is alpha, which is the weightage given to the loss term. So the joint training, so we have task loss and then this proposed joint training loss, right? So alpha is the weightage given to that loss. So you can see alpha equals, so 0.7 is actually the best performing alpha here. So it's 0.7 here as well. Mostly 0.7 is the best performing alpha. And this is the attention distribution visualization. So it does not eliminate over-globalization, but it kind of reduces, right? So this is the attention, so after this joint training, right? So yeah. So you can see that downward trend from k equals 4 onwards, k equal to 4 or 6 onwards. Yeah. So this is for the homophilic data sets. You can see a similarly looking downward trend here as well. Yeah, so this slide summarizes the future work of this research paper. Yeah, so as I said, so mitigating over-globalizing specifically for heterophilic graphs is one line of future work. So as Professor suggested, so there is that interesting back and forth trend, right? So which is kind of revealing. Maybe it talks about the bipartite structure of the input graph. So that is left for future work. So this is one line of future work. And it is observed that two-hop neighborhoods are actually the most informative in heterophilic graphs. So maybe we can actually use this information somehow to design a graph transformer. So that could be one line of research. Yeah, so a two-hop GNN plus a graph transformer. So that could be one potential idea for looking at over-globalizing on heterophilic graphs. And then there are no standard metrics for over-globalizing. So K-hop homophily is not really a metric. It's like a visual comparison between K-hop homophily and attention distribution. So there is no concrete metric for over-globalizing. So something that says over-globalizing is high on this task, over-globalizing is very low on a different task. So there is nothing that says, so there is no metric that has been proposed in the literature. Right? So this is one line of research. And then there are some issues with local models as well. So graph neural networks, they have their own issues. Some of them are actually over smoothing and over squashing. So these are different issues that happen because of the local nature of GNNs, right? So one line of research could be to see if joint training can kind of jointly reduce over-globalizing and issues that are specific to GNNs, like over-smoothing, over-squashing. That is another line of research. Okay, so this slide summarizes all the interesting future extensions of this research. And yeah, so I'm actually done for the talk. So yeah, thanks a lot for listening.